A yo-yo is being swung around downward at an angle of 37 degrees relative to the vertical. If the string is 0.8 meters long and the yo-yo is 0.85 kilograms, how fast is it traveling? We're going to see a few problems like this. And what's happening is an object is attached to a string. In this case, it's a yo-yo. It's being whirled around in a horizontal circle. So the motion of the object itself is horizontal. The twist in the problem is that it's being swung at an angle. In this case, it tells us that the angle is 37 degrees relative to the vertical. And if you recall from when we were doing forces, we call that phi. So phi is the angle relative to the y. It tells us that the string is 0.8 meters long, so that's referring to the length of the string, not the actual radius of the circle, so I'm going to call that L. And then it tells us that the yo-yo is 0.85 kilograms. So let's just list what we were given. And there are the three things I just mentioned. So the angle relative to the vertical, phi, is 37 degrees. The length of the string, L, is 0.8 meters, and the mass of the yo-yo, M, is 0.85 kilograms. Before diving into the problem, what we need to do is figure out what this L means and how it actually relates. So again, this is hard to draw, but this is a horizontal circle. So the yo-yo is just it's not gaining any height. So up or down, it's just moving in a horizontal circle. So the radius of this circle, is that. And I'm trying to draw this as three-dimensional as possible. It's not exactly easy. So let's just look at this as a triangle. You have the length of the string, L. This dotted line represents the vertical. This is the angle, phi. Yo-yo's over here. It's moving around a horizontal circle with a radius r. So maybe if I draw it a little bit more like this. So this is the circle going around. I'll do that in a different color. So the circle is the one in green. The radius of the circle is from here to here. The length of the string is the hypotenuse of this little triangle, and this angle phi is the one relative to the vertical. So we have the angle phi, we have the length L, we're looking for the radius. The reason being any kind of centripetal equation, so for acceleration or force centripetally, you need the radius. Looking at this triangle, we're given the angle phi, and it's okay to use that. We don't have to change around the angle for this part. We're given the angle phi, we're given the hypotenuse, and we're looking for the opposite. So we want to use sine. Sine of phi is equal to opposite over hypotenuse, so the radius over the length of the string. So the length of the string times the sine of phi will give me the radius. 0.8 meters, sine of 37 degrees equals radius, and this equals 0.481 keeps on going meters. I would store that in your calculator as r. So we know that our radius now is 0.481 keeps on going meters. Again, we want to use the unrounded number. I could have also used cosine. So if this is my triangle, this is the angle phi. The angle relative to the x is theta. So you could have done sine using the phi, or know that cosine of theta is equal to r over L. So L cosine theta would equal the radius, 0.8 meters. Cosine, remember theta is 90 minus phi, so this would be cosine of 53 degrees equals r, and you're going to get the same exact number, 0.481 keeps on going meters for your radius. So it's up to you whether you want to use sine or cosine in order to find this radius. But know that for problems like this, where something has an angle relative to the vertical, but it's being swung in a horizontal circle, you're going to have to do some trig to figure out what the actual radius is. So we're given this angle phi, we're given the length, we used those two things to figure out what the radius was. We were also given the mass. What do we want to find? It's asking us for how fast is it traveling, so we're looking for speed. Let's look at the force diagram. We had a similar problem on worksheet 1 where a plane was banking a turn, and when we drew that force diagram we had a lift force. And I used the plane on the string to demo what this looked like, so this is a very similar problem, just now with numbers. So the yo-yo is being swung around in a circle. It's being pulled up and to the right the way I drew my diagram by a tension force. And because it has mass, it's going to have a weight. The center of the circle is over here, so that must mean that the net force or centripetal force has to be directed towards the center. If I break apart my tension force into its components, we get Ftx and Fty. That cancels out Ft. The angle it gave us was the angle relative to the vertical, so that was the 37 degrees. The angle relative to the horizontal is 53 degrees right there, so theta and phi. Fty should equal Fg because it's not accelerating in that direction, not accelerating except towards the center of the circle. And we know that Fty is equal to Ft times the sine of theta, and Fg we know is equal to mg. Looking at the force diagram, the only force directed towards the center of the circle is my x component of the tension force. So Ftx is equal to centripetal force. We know that Ftx is equal to Ft cosine theta, and that Fc is equal to mv squared over r. I've got two equations, 1, 2. I've got two unknowns. We don't know Ft, we don't know V. So two equations, two unknowns. We're going to do a system of equations and set them equal to each other. Because it's not asking us for the tension force and it is asking for speed, what I'm going to do is eliminate the Ft's. So let's isolate both of these Ft's in the equation. The first one, Ft is equal to mg over sine theta, and the second one, Ft equals mv squared over r cosine theta. So just dividing by the sine for the y and the cosine for the x. Setting these equal to each other, we get mg over sine theta equals mv squared over r cosine theta. M's cancel. The only unknown in this whole equation is the v. So let's do our algebra. We get r cosine theta g equals v squared sine theta. R cosine theta g over sine theta equals v squared. So coming up here, radius, you should have stored that number in your calculator. 0.48 keeps on going, meters. Cosine of theta, 53 degrees, times 9.8 meters per second squared, whoops, ran out of room, over sine of 53 degrees equals v squared. Multiplying this, we get 3.55, keeps on going, meters squared per second squared, equaling v squared. Square root of that, 1.88, keeps on going, meters per second equals v. So only one sig fig, the speed is approximately 2 meters per second. If this made sense to you, fine, I'm glad. I'm going to solve it again 2 more times just to show you 2 other ways that this can be solved. So again, if this is okay, then you're good. I'm going to solve this 2 more times. We're going to keep these 2 equations the same. It's this part down here that's going to get a little bit different. So just showing you what can happen with the trig. So again, if you're okay with this, fine. If you want to see the 2 other ways it can be solved, keep on watching. Okay, so the second way to solve this, and again, everything up to the steps where we're isolating ft is the same. We end up with, mg over sine theta equaling mv squared over r cosine theta. So looking for v, again, because this is the only unknown, masses cancel. We get rg cosine theta equaling v squared sine theta. Divide both sides by sine, so rg cosine theta over sine theta equals v squared. And if you remember your trig, cosine over sine is equal to cotangent. So rg cotan theta equals v squared. So this is always going to be true for any kind of problem like this. And what I mean by that is anytime you have a horizontal circle but the object is being pulled on by a force at an angle. So v will equal the square root of rg cotan theta. So this is the second way to solve. Instead of leaving it cosine over sine, just making that into cotangent of theta. Putting the numbers in, you'll get exactly the same answer. The 1.88 keeps on going meters per second. The third way to look at this, and we're going to have to backtrack a little bit. Whenever you have a triangle and your angle relative to the x is theta, your angle relative to the y is phi, you know that tan theta is the same as cotangent of phi, and vice versa. So cotangent of theta equals the tangent of phi. So if we were to go back and get to this step right here, where rg cotan theta equals v squared, cotan theta is the same as tan of phi. So we can say that rg tan phi equals v squared. So v equals the square root of rg tan phi. Again, where phi is the angle relative to the vertical. This always works. This always works. Keeping it in terms of sine and cosine always works. So it's up to you how you want to approach this. Yes, you can memorize it because again, this will always work. No, this will not be an equation that I give you on the formula sheet. So you can use the cotangent of the angle relative to the x, you can use the tangent of the angle relative to the y, or you can just keep it in terms of sines and cosines. All 3 of these ways should get you the exact same answer.